This video is produced by the UCD Math Support Centre in conjunction with the UCD Access Centre. In this video we will be looking at proof by contradiction and how to use that to prove that root 2 is irrational. In the previous section we looked at rational numbers and we defined them in such a way that they were numbers that can be written as a fraction of two integers. So that is, x is rational if we can write x equal to a over b, where a and b are both elements of the set of integers and b is not equal to 0. We can naturally arrive at the conclusion that an irrational number is any number for which we cannot do this, so we cannot represent it as a fraction of two integers. An important thing to note is that every fraction can be reduced to a lowest form. For example, 8 over 28 is equal to 4 over 14, which is equal to 2 over 7. The last of these fractions is in its lowest form. It cannot be reduced any further. We say a rational number is in its lowest form when the numerator and denominator have no common factor apart from 1. And we can see if we wanted to try and find a number that would divide both 2 and 7, the only number is 1. So proof by contradiction is a useful method for proving mathematical statements. So the idea is as follows. We begin with our statement of a theorem. We assume that the opposite of this is true. And with this assumption, we will then try and do some basic mathematics and see what happens. Eventually we will arrive at a contradiction, a point in which the mathematics breaks down and things don't make sense anymore. The only resolution is that the initial assumption that we made must have been wrong, proving that the original statement is true. So we will now see an example of using this method to prove that root 2 is an irrational number. So if we want to prove that root 2 is irrational, we want to assume the opposite. So we will assume that root 2 is a rational number and thus can be expressed as a fraction of two integers in its lowest form. So we will allow root 2 to equal to a over b, a rational number, and we will assume that a and b have no positive common factor apart from 1. So our assumption being that root 2 is now a rational number and can be written as a fraction. If this is true, we can square both sides to find that 2 is equal to a squared over b squared. So squaring both sides of root 2 is equal to a over b gives us this line. Continuing with this, we can rearrange to find that a squared is equal to 2b squared. So multiplying both sides of the previous equation by b squared. This implies that a squared is even, since it is clearly divisible by 2. As we can divide the right hand side by 2, it means a squared must also be divisible by 2. Now the square of an odd number is odd, and the square of an even number is even. So if a squared is an even number, this implies that a is also an even number. So we'll need to remember that fact, that a is an even number. What this means is we can write a is equal to 2 times k, where k is some other integer. The reason we can do this is if a is an even number, it can be 2 times another number, as 2 is an even number. So going back and looking at 2b squared is equal to a squared. Instead of a, we can sub in 2k. So now 2b squared is equal to 2k all squared. And 2k all squared is equal to 4k squared. What this means is we can write b squared is equal to 2k squared. By the same reasoning as above, this would imply that b squared is even. And again, as b squared is even, b is even. And herein lies the contradiction. So we assumed that the square root of 2 is equal to a over b, where a and b have no common factor except 1. What we have done is showed that both a and b are even, meaning both of them have a common factor of 2. What this means is we could divide both a and b by 2, meaning the fraction a over b is not in its lowest form, which is our contradiction. So this gives us that root 2 must be irrational.